Hello guys, welcome to the portal. Uh, in this video we are going to talk about Doppler effect with sound. Okay, remember on the last video we talked about the reversion of electromagnetic waves, and we talked about that there are two types of Doppler effect: the Doppler effect with sound and Doppler effect with light. Now we are going to focus on Doppler effect with sound. Okay guys, have you ever experienced this? You are standing at a traffic light and then there's an ambulance approaching with its siren on, emitting sound waves, and then as the ambulance is approaching you, you notice that there's a change in the way the siren sounds, and as it is moving away from you, there's also some change that you can hear in the way the siren sounds. So as the ambulance is approaching, you will notice that the siren, sound the sound waves, like they are, they are coming to you like at a faster rate. But as it is moving away, the sound becomes a bit, slow, as the siren moves away. So now, whatever that is happening there, it's due to a phenomenon. It's a phenomenon named the Doppler effect. Okay, so now we have two things that we want to focus on when we talk about the Doppler effect. So what are these two things? We have the source. Okay, the source. What is the source? Is the source of sound. In our example, the ambulance that is blowing the siren there. Okay, and what is the other thing? We have the observer, which is the listener in this case of our example. So you are the one who's hearing the siren from the ambulance, which is the sound source. Okay, so this is the little closer that you guys might find handy, because you find that I will talk about the source, the listener, or the observer. So you must know, when I talk about the source, I'm talking about the thing that is emitting the sound waves, and the observer is the person hearing the sounds, or at times a detector, a sound detector that is placed at some point to record the waves that are being transmitted by the sound source. Okay, so here I have a scenario whereby I have a source of sound. Okay, so let's say this is our ambulance. So our ambulance is standing, it is stationary at a traffic light. Okay, so now the traffic light is what is red. So because our source is stationary, our source has a velocity. The velocity of the source, we say, is vs. So vs is equals to 0 at this point. Okay, so now at the other side, on the other side of the traffic light, there's observer 1, which is Lesedi. So Lesedi now is also not moving, stationary. So with velocity VL, for velocity of the listener, okay, VL1, let me name it VL1. So the velocity of the listener is also what? 0 meters per second. Okay, and there's Isaiah on the other side. Isaiah is also not moving, so let me name it VL2. So Isaiah is not moving, so the velocity of Isaiah is 0 meters per second. Okay, so now both Lesedi and Isaiah are observing the waves emitted by the sound wave the same, because they are, you know, they are both stationary, and the sound source is also stationary, and they are almost equidistant from the sound source. Okay, so now you will notice that here I have sound waves. Okay, let me name this sound waves. Let's say now this is what is our, this is our trough, and the yellow one is our crest. Okay, so now we have yellow crest and green trough. Okay, so as the siren it's playing there, they're observing the sound waves. Okay, so this is the waveform of the sound waves. Okay, so now excuse my drawing, but this waveform is meant to be constant. Okay, so everything here is the same, everything is constant. Okay, so now if I can say, okay, let's check the frequency and the period of the waves observed by Lesedi and Isaiah. Okay, so if now I can say what is my wavelength, my wavelength will be between the two troughs. Okay, the two green lines. Okay, so between the two troughs, so I will have what, I will have my wavelength. Okay, I'll have my wavelength. All right, and then also here I have my wavelength. I have my wavelength. So now you will notice that the wavelength of the waves observed by Lesedi is the same as the wavelength of the wave observed by Isaiah. Okay, so now it means now they're observing the same frequency of sound emitted by the source, and they're also observing the same frequency that is emitted by the source. Yes, I said that. Okay, so now what I talked about the wavelength. What about the frequency? What can I say about frequency from this information? We know from the previous video that we discussed about the relationship between frequency and what, and wavelength. Okay, so frequency is equals to the speed of sound divided by the wavelength of the sound wave. So now from this we can see that there's inverse proportionality between the wavelength and the frequency. So meaning that if my wavelength increases, the frequency will decrease, right? Okay, so now, but because both Isaiah and Lesedi are observing the same wavelength, it means that they are observing the same frequency. So if this sound source emits the sound waves with frequency, let me put it as yellow, with frequency fs. Okay, and then Lesedi is observing the same frequency. Is the frequency observed by Lesedi is what, is FL1. Okay, and the frequency observed by Isaiah is what, is FL2. Okay, so now because of they have the same velocity, the source and Isaiah and not and Lesedi, because they have the same velocity, so both Lesedi and Isaiah will observe the same frequency of sound as emitted by the sound source. Okay, so now the frequency observed by Lesedi will be equals to the frequency emitted by the sound source. So there will not be any difference. Okay, and here also they will observe the same frequency. Alright, but as soon as now the traffic light turns green, the ambulance starts moving, right? So the ambulance will move away from Lesedi and move towards Isaiah. Now we'll have something different now. Okay, we'll have something different. You will notice that as now our ambulance is moving, at a constant velocity v, all right? So what vs, the speed of sound. And then now our source of sound is moving, so the speed of the sound source, I'm sorry, it's not the speed of sound, it's the speed of the sound source. Okay, so now both Isaiah and Lesedi, they are stationary, they are still stationary. So Isaiah's velocity is what is 0 meters per second, and also Lesedi's velocity is what is 0 meters per second. But then now our sound source is moving, it's moving at speed v that we don't know about yet. Okay, so now you notice that the waves in front of Isaiah, they are compressed. Okay, and then the waves between the city and the source, they are being distanced a bit. The space between the consecutive troughs has increased. Okay, so now remember that distance wavelength is between two troughs or between two crests. Okay, so meaning that here now the wavelength will be between this okay, this is a trough. Okay, between this trough and this trough. Okay, this is the wavelength, and also from this from this crest. Okay, so now also, okay, in here we have also have the wavelength. Okay, so you notice that Isaiah is observing a wave which has a shorter wavelength, and Lesedi is observing a wave which has a longer wavelength, right? So meaning now they don't observe the same wavelength of the wave. But how will they observe the difference? They will observe the difference by what? By the frequency of sound. So remember that the frequency is related to what? To wavelength, meaning that Isaiah will observe what? A higher frequency, and then Lesedi will observe lower frequency. So now Isaiah will observe a wave which has a frequency that is greater than the frequency of the source. So now, and then Lesedi will observe frequency that is less than the frequency of the sound source. So as you can see from from this situation whereby the sound source is moving towards Isaiah and away from Lesedi, you can see that now the frequencies observed by each person, they are different compared to the frequency emitted by the sound itself. So if you check the scenario above, all of the points of interest, they have the same velocity, which is the velocity of what, of zero. Okay, so the source has the same velocity as the observer, and also as Isaiah. Okay, and also the source has the same velocity as Lesedi. So now here there's no Doppler effect. Okay, so now, and then here, because now there's a difference in velocity when you compare the source and each observer, you see. So because of there's a difference in velocity, now there's a difference in observed frequency as compared to the one that is emitted by the sound, you see. So this phenomenon is called Doppler effect. So here's the definition of Doppler effect. It is the change in frequency and pitch of the sound that is detected by the listener. Because the sound source and the listener have different velocities relative to the medium of propagation. Okay, you can read that again. But then now, let me use my highlighter. Okay, so now the key words is what the change. Oh man. Okay, where is that highlighter? The, the change in frequency and pitch of sound that is detected by the listener. Here on detected you can also use observed. So now because the sound source and the listener have different velocities relative to the medium of propagation. So now you have noticed from the above, the first scenario, they had the same velocities, but then FL and FS, they were the same as well. And here in the second scenario, they had different velocities. So that's why there was a change in frequency of sound that is detected by both Lesedi and Isaiah. So now the medium of propagation, they are talking about, for example, air. As the siren is emitting waves, is emitting the waves that are being emitted are traveling through air. So the medium of propagation here is air, and the speed of sound in air, it is usually 340 meters per second. So when we are in the medium, so that is air is what the medium. Sorry about that. So that air, now it is our frame of reference. That speed of sound in air is our frame of reference. So everything that, every other velocity that we are looking at, we are looking at it relative to the medium of propagation, which is our frame of reference. Okay, so now this Doppler effect, mathematically, it is explained. It is explained by this equation, or this formula. Rather, let me say this formula. It is explained by this formula. Frequency of the listener, or the frequency observed, is equals to the speed of sound in whatever medium that we will be propagating the sound waves in. Okay, plus minus velocity of the listener or the observer over the same speed of sound in a respective medium, plus minus the speed of the sound source multiplied by the frequency of the sound source. So let me make something clear. The frequency of the sound source does not change, Right. So in these situations, the frequency of the sound source does not change, but what changes? The frequency that is being heard. So the people who are hearing the frequency, they hear a different frequency than the one that is being emitted by the sound source. So reason being, there's a difference in speed between the sound source and the listener, or rather the observer. Okay, so now let me explain each terms here. So now FL is what? It's a frequency observed by the listener. What about FS? FS is the frequency emitted by the sound source. It's actually the frequency of a wave emitted by the sound source. Okay, let me just say frequency emitted by sound source. Alright, so and then V is the speed of sound in a respective medium. The medium can be in blood, the medium can be water, the medium can be air. We'll talk about this blood medium on later stages, on where we can use Doppler effect, while we work with blood. Okay, so now what's left? Okay, VL. What is VL? VL is what? The velocity of the observer or the listener. So velocity of the listener, velocity of the listener or observer. What about VS? Velocity of the sound source. Velocity of the sound source. Alright, so now we've only talked about two scenarios whereby the source is the one that is moving. Okay, whereby the source is the one that is moving. So I want to talk about a scenario whereby the observer is the one that is moving, but the source is stationary. Unfortunately, I will not have time to draw it. So I will refer to a textbook that anyone can access, a Siavula written by volunteers. Okay, yeah, here's the situation, here's the scenario. Okay, here, if you look at this scenario, for example, here, okay, you will see that we have a source. You see that we have a source here. Sorry, we have a source. We have a source here, and then we have two observers. So this observer is facing away from the sound source, which is the police car, and this observer is facing the head of the police car. So now we can tell that if now these two observers, they will start to move, this one on the right would move towards the police car, and this one on the left would move away from the police car. So now as the police car emits sound waves, this is what is happening. Now, if this is the crest, the yellow, if this is the trough, the yellow one, and the number two, wave number two is the, the this is the crest, and this is the trough, and then a trough crest. So now you'll notice that as the person on the left moves away, how many waves will he experience from his position? He will experience only not a lot. So, and then here he will only experience this 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 trough, this crest, and this trough. So you will experience two, but two troughs. Almost there are two troughs, and what and one crest. But what about this one? You will experience one, two, three, four. You will experience two troughs and two crests. So what I'm talking about is shown there. Let me enlarge it. Enlarge it. Okay, it is shown here. So this person who's moving from wave from 1 through 7, and this one is moving from 7 and to the other direction. So now this one you can tell that is going to experience a lot of waves per unit time, and this one is going to experience lesser amount of waves per unit time. Why is that? Okay, they are moving at the same time. Okay, they are moving at the same time, and let's say they're moving with the same velocity. So now the observers, if they are moving at the same velocity but their velocity is different to the velocity of the sun source. Okay, so now this one from the right, the one that is going towards the car, experiences the sound that has this wave, and then the one who's moving away experiences only this part of a wave. So now we know that if I have more waves passing a fixed point per unit time, what does that mean? It means that my the frequency will be high, because frequency is what complete waves passing a fixed point per unit time, right? So here the frequency will be here the frequency will be low, and here the frequency will be high. Okay, so now when the observer is approaching a sound source, the observer will observe a frequency which is higher than the frequency of the sound source, and when the observer moves away from the car, the observer will observe a frequency which is less than the frequency emitted by the source. Okay, so now let me summarize it here. So so let's say I have two scenarios. I have scenario number one, right? So the source is moving, whereby the source is approaching. Let me start by saying the source is moving, whereby the source is moving. Okay, it's scenario number one. So what happens when the source is approaching a stationary observer? So what happens is, now the frequency observed by the listener or the observer will be greater than the frequency of the sound source. And then when the source is moving away, moving away from the stationary observer. Now the observer will observe a frequency which is less than the frequency of the sound. Okay, so now scenario number 2, as I was showing you from the textbook, the observer, okay, or what you might say, the listener, okay, moving. So now in grade 12 we are only focusing on the Doppler effect, whereby one of the two between the observer and the source is moving. If one of them is moving, the other one is stationary. Okay, so you don't have to worry about what if they are both moving. So now what will be the frequency when the observer approaches, when the observer approaches a stationary sound source? What happens now? The frequency observed by the listener is greater than frequency of the wave emitted by the sound source. Okay, and then observer moving away. So moving away from a stationary sound source. So now also here the frequency observed by the listener will be less than frequency emitted by the sound source. Okay, so now we can use this Doppler effect formula to show all these aspects that I'm talking about. Okay, so now from scenario number 2, whereby the observer is moving, the key thing is that the observer that is approaching, when the observer is approaching the sound source, the observer records many waves per unit time. Okay, and then when the observer is moving away from the sound source, the observer observes fewer waves per unit time. And you know, the more waves we have per unit time, it means the higher the frequency, and the lesser wave we have, the lower the frequency. That is the key. Now, and then the key here on the source number 1, or on scenario number 1, the key is what? The difference, also the difference in what? In wavelength, right? And also wavelength is related to what? Is related to frequency. So you will notice that you will remember from grade 10 that if I have excuse my drawing. Okay, if I have two waves here, if I have two waves, let's say this wave is like this, and then I have another wave here. So if the total time here is what? It's 1.0 second, and here it's 1.0 seconds. Let's say this is it's pressure, this side, pressure. So now what happens in scenario number 1 is this: when the observer is stationary and the sound source is approaching. So here the sound source is approaching, right? Then here the sound source is what? Moving away. It's what we are observing. Remember, it's what we are observing. When the sound source is moving away, we have the wavelength that is stretched. And then when the sound source is approaching the observer, we have the wavelength that is compressed. So now, let's compare the frequency of these two waves. So if you can check now, here, we'll have some time. Let's say the time here is 0.7 seconds, right? And then now, remember what is a period? So period is what is whereby a full wave passes a fixed point, right? Is a time whereby a full wave passes a fixed point. So now the period of this wave will be 0.7 seconds, right? But here the period will be much lesser than 0.7 seconds. So in this wave we can say we have a longer period, right? And then in here we can say we have what? A shorter period. A shorter period, right? And then now longer period corresponds to what? Corresponds to lower frequency. Remember that period and frequency, they have they are inverse relationship. So when period becomes longer, the frequency becomes lower. Also here, it's what is happening. So the shorter the period, the higher the frequency. Okay. Also wavelength. With the wavelength in this part, if on my time axis, if I had this, if I had distance, it was going to be shorter. It was going to be shorter wavelength. Okay. So but now because I have second, I have time, so I'm talking about period. Okay. So meaning here I have what? I have higher frequency, and then in here I have what? Lower frequency. Okay. So now let me give you a summary on the Doppler effect, uh, on the Doppler effect formula, and how you're going to use it, because we can see this plus or minus, plus or minus. I mean, how are we going to use that? So let's try and see how this is going to work. Okay. So now from scenario one, whereby the source is moving, right? So now source approaching, source approaching. So if I use the same formula, right? So before you do anything, even in your calculations, you must rewrite the formula as it is. Okay, guys, you must rewrite the formula as it is. So how is our formula going to be now? When the source is approaching, the velocity of the sound source is what? It's something that we don't know. Okay, and the velocity of the listener is what? Is 0. Okay. So now what's going to happen? We will have FL is equals to V plus minus 0 here. Okay. Over. So V. So which one are we going to take here? Remember now, the source is approaching, and when the source is approaching, we are expecting the observer to record a frequency which is higher than the frequency emitted by the sound source. So in order for us to have some a value, the fraction, remember that this is a fraction. In order for us to have a fraction that is larger, right? So it means that the numerator must be greater than the denominator. Remember that V is the same as V. Okay, it's the speed of sound in a respective medium. So now it means now we must have a smaller denominator. Okay, so in order for us to do that, we are going to choose the negative side. So now what do we have? Okay, let me write it very nice. We have that. So now we have a numerator that is greater than the denominator. Now it means that we are going to multiply fs by a number that is greater than 1. So that guarantees that we're going to get the observed frequency that is greater than fs. Okay, so now, and then what about when the source is moving away? So when the source is moving away, we are going to observe this. We must observe the frequency of the listener must observe the frequency which is less than the frequency emitted by the source. So remember that the listener is stationary, so VL is equals to 0. So here we have V. Now because we are expecting VL to be less than we are expecting FL to be less than FS. So now our fraction must be something that is less than 1. So in order for us to achieve that, we must put positive. Okay, so now here we have a numerator that is less than the denominator. We have what? A proper fraction. So now we'll have a decimal when we multiply a number that is less than 1 by this value. So the result will be a result which is less than fs itself. Okay, so now number 2, scenario number 2. On scenario number 2, the observer so what moving is moving. Okay, now if the observer is moving, the observer can approach the source. Okay, so what happens when the observer is approaching the source? How will our formula be? So now the observer is the one who is moving, so VL is no longer 0, but what is 0? Vs is 0, so we only have V at the bottom. Okay, so here will it be plus or minus? Think about it. So when the observer is approaching, remember, observer perceives more troughs or more crests per unit time when the observer is approaching the source, right? So meaning that the perceived frequency will be higher than the frequency of the sound source. So it means we must have a fraction that is improper. So here it must be plus. Okay, so now what about this part? Now here we will have let's say now the observer is moving away from the source. Okay, so the observer is moving away from the source. So now how will the frequency graph be like? So it will be V minus VL all over V. Okay, so when you come with this derived formulas, before you write the derived formula, you must write the formula from the formula sheet from the question paper, because if you just write this, you might get penalized. Okay, so and you might make mistakes and you find that you forfeit the mark of the formula. So please write this formula as it is, copy it from the formula sheet, and then from there you're going to write this, because when we calculate we will use this, because on the calculator you can press plus and minus at the same time. Okay, so let me give you a summary, because I know we like to make things easy, we don't like it when things are difficult. So now these are the scenarios. So here I have a scenario, so let's summarize it. So now here is what? Source approaching, source moving away, and then observer approaching, observer moving away. So now I have VS and I have VL. Okay, so now when the source is approaching, it means the source is moving. When the source is moving, the observer is stationary. So now the sign of the source, the sign of the source of Vs, it must be what? It must be minus Vs. And then when it is moving away, it must be plus Vs. Okay. And what about when the observer is approaching? Vs is 0. And then what about VL? VL must be plus VL. And here, minus VL. Okay, so this is your summary of the signs used in the formula. Okay, so we can't just talk about formulas without doing an example. Okay, can't just talk about formulae without doing an example. So let's have an example, one example. One example. So now let's say a police car moving towards Elena, a police car moving towards Elena, standing at the school's gate. School's gate. Is moving at a constant velocity of 10 meters per second. Right? And then now the siren on the police car emits waves of constant frequency of 600 hertz. Okay, so that is a statement. So now the police car moving towards Elena, standing at the school's gate, is moving at a constant velocity of 10 meters per second. The siren on the police car emits waves of constant frequency of 600 hertz. Right? Now, the question now, calculate the frequency observed by the learner. Calculate the frequency observed by the learner. Okay, so what will you do? First things first. There's an information that is missing. Okay, now assume the speed of sound in air is 340 meters per second. So now, before you do anything, you write the formula. You copy the formula from the back of your question paper. it will be written like this. Okay, so now after copying the formula, that formula will get 1 mark automatically if you have copied it correctly. Okay, now what are we going to check? We are going to check the data that is given in our statement. First of all, we must check what scenario we are having. Here we have a scenario whereby the police car is moving towards. So what is towards? Towards is approaching. Okay, so the police car is approaching the lane. So we must expect that the frequency observed by the learner will be greater than the frequency emitted by the sound, the frequency of the waves emitted by the sound source. Okay, so now which are we going to take? Which sign are we going to take here? So the source is approaching, so we are going to take minus Vs. Okay, so now another information that we have is that the liner is standing, so meaning the liner is stationary. Okay, and another information, so it's what constant velocity of the sound source of what 10 meters per second, and what and frequency of the sound source 600 hertz. Okay, so information, we must identify the information that we have. Data. Okay, data. So now Vs is 10 meters per second. What about VL? VL is 0 meters per second. V, they said assume speed of sound in air is what 340 meters per second. So what about Fs? They said it's 600 hertz. Okay, so from this formula we have Fs, we have VL, we have Vs, we have V. What we don't have is what is FL. So let's go and calculate. So now we can use this formula directly as it is. Okay, so FL is equals to, so now going back to the scenarios, when the observer is stationary and the source is approaching the observer, it's scenario number 1. So the formula is FL is equals to V over V minus Vs multiplied by Fs. So V over V minus Vs multiplied by Fs. So now what are we having here? We're going to have V is equals to 340 meters per second over 340 minus 10 meters per second multiplied by what? 600 hertz. Okay, so now you do the calculations. Okay, I'll give you some time to do the calculations. Okay, now so now let me do mine. So I am getting FL is equals to 618.18 hertz. So now as you can see, frequency observed by the listener is greater than frequency emitted by the sound source. So now you can tell that our answer is correct, because the frequency observed by the listener is greater than frequency emitted by the sound source. Okay, so now we will do more examples. So I will end this video here so that we can save data. Okay, so but I'll do more examples and more content in our next video. Okay, thank you.